Thank you. Thank you for Amy for the introduction. Today I'm Lawrence, and I'm a PhD student from Cornell. I work with Professor Michael Lipson at Cornell University. And most of the work I'm going to be talking today would be collaboration with Professor Xianghui Fan at Stanford University, and also with Professor Paulo Nelson-Spey at University of São Paulo. And today I'm going to talk to you about what is photonic transitions, and what does photonic transitions do to the photons, and that would enable an effective magnetic field for light. And the experimental demonstration will be all on an on-chip platform, so hopefully in the end I'll convince you that this will be a viable path to create an effective magnetic field for light using silicon photonics or integrated photonics. So I first want to throw out a question to the audience. Will a magnetic field interact with photons? The answer is pretty obvious, because in a very fundamental level, photons are neutral particles. They're not electrons, so they wouldn't interact directly with a magnetic field. But however, the photons do interact with the magnetic field indirectly through the use of magneto-optical materials, for example. So these are the kind of works demonstrated on the on-chip platform using magneto-optical materials. And these are basically Faraday rotator crystals. And what these little crystal does is, when you apply external magnetic field, it will change the refractive index of light, and therefore that's why I mean by interacting with photons indirectly, because it's changing the material property and then induce a change on the photons. And there's considerable interest in integrating these magneto-optical materials on chip these days, mainly because people are gaining interest in developing on-chip lasers for telecommunication or other application purposes. And for these lasers, usually you need isolator right after it to protect any back reflections that would cause the laser line wavelength and power to fluctuate. And so there's a considerable amount of research that's been done in this area. And however, to integrate these magneto-optical materials on chip is fundamentally challenging. And for example, you can do wire bonding, you can do wafer bonding or chip bonding, like the first two figures on top. And the bottom figure is a monolithically integrated, basically directly depositing these MO materials directly on the silicon wafer. But for these kind of approaches, these magneto-optical materials usually have much lower quality than single crystals, which is very apparent. And in general, these magneto-optical effects in the optical domain is generally weak. And so we want to ask a different questions among ourselves is, can we actually generate an effective magnetic field directly coupled with photons? And we want to do this on chip, and while not being limited to using the magneto-optical materials. And I will show you the applications later. I just want to first show you what is an effective magnetic field, and what do I mean by having effective magnetic field for photons. So we all learned from classical electromagnetics, magnetic field equals to curl A, where A is the gauge potential. And in quantum mechanics, we also learned that electrons actually interact directly with the gauge potential instead of the magnetic field, B field. And this is being shown in the second equation, where in this equation, that the non-spherical phase phi will be introduced to electrons as it travels through a gauge potential, a gauge field, a field. And this non-reciprocal phase just comes from the fact that this is a line integral. So the key here is for photon to possess a effective magnetic field. So the key is to first try to find a way to create this non-reciprocal phase, this phi phase. So what we can do, once we find the non-reciprocal phase, this phi non-reciprocal, then we can write an equivalent effective gauge potential for photons, which is this A effective. And the effective magnetic field for photon, which just simply means phi curl A. So the key is now we want to find a non-reciprocal phase for photons. If we can find the non-reciprocal phase for photons, we can get a effective magnetic field for photons. And what do I mean by this effective magnetic field to photons? What does it do to photons? So basically, it should do the exact same thing as if electrons are experiencing a real magnetic field. So for example, so you imagine electrons traveling in a uniform magnetic field would experience a Lorentz force. So therefore, electrons would bend in this material. But if we arrange these non-reciprocal phases in this 2D array fashion, we are effectively generating a uniform magnetic field. In this case, the magnetic field is uniform. And so in this left image, you can see the non-reciprocal phases are arranged in a 2D array, and they have different numbers to our signs just to create this uniform magnetic field, effective magnetic field. And based on simulation from our collaborators, you'll see the similar effect like electrons. So photons incidenting from the left of this edge will start to curl, and just like experiencing a real magnetic field. So this is a very unique way that potentially, if we can do this on chip, we can steer light on chip using this effective magnetic field if we can generate these non-reciprocal phases. And there's another example, which is and these non-reciprocal phases, if we can control it, which means that we can create this effective magnetic field arbitrarily, the effective magnetic field doesn't need to be uniform. So for the bottom image, the bottom left image over here, the effective magnetic field is created right in this boundary, in this slit. So we're creating a boundary of this effective magnetic field, and you might already guess that whenever you have an optical structure that has a boundary, you create refractions and reflections. And in simulation, you do see these reflections and refractions happening. And I have to remind you that because these non-reciprocal phases breaks time reversal symmetry, so that all these effects we see here, when you change the direction of light, it would behave very differently. So there's other interesting phenomenon when you have these non-reciprocal phases. For example, just like electrons interacting in a material, electrons in a material interacting with very strong magnetic field, you'll start to see topological effects. When we say topological insulators for electrons, so which means electrons cannot when electrons interact with a strong magnetic field, it cannot travel through the bulk of the material, but it can only travel through the edges of the material. And the edge, the shape of the edge, and any disorders on the edge will not affect the trajectory of the electrons. Electrons still can go around these scattering disorders and staying on the edges. And this is also true if we arrange these non-reciprocal phases into this array fashion. And if we have a stronger effective magnetic field, we will start to see photons also exhibit these edge states. So you can see light can only travel around these edges, and these edge modes are only one way. There's only one edge mode exists. And if you have any disorders, such as like this, maybe in your fabrication, you have slightly larger resonator width, so light wouldn't couple into those resonators, but the edge mode still exists, so the edge mode will travel around these disorders and move forward, and hence the name of photonic topological insulators. And I want to mention that there's a lot of demonstration on these photonic topological insulators very recently, but these devices are all passive devices, which basically means that there's edge states, edge modes moving in the clockwise direction, and also one edge mode moving in the counterclockwise direction. So now they can only protect this array of geometrical disorders, but they cannot suppress backscattering, which light can couple from the forward edge mode to the backward edge mode. So basically, these works do not provide full topological protections. So another thing very interesting is isolators, because since we're already generating these non-reciprocal phases, so it's natural to think of we can just make an isolator. So there's a lot of recent works trying to demonstrate isolators without using magneto-optical materials for the reason I talked about earlier. And however, all these work did not demonstrate, at the very fundamental level, did not demonstrate an effective magnetic field directly coupled to photons. So now let's go back to the non-reciprocal phase. So now we want to find in what kind of photonic structure can we generate this non-reciprocal phase. And if we can generate this non-reciprocal phase, again, we can write effective gauge potential that can relate it to a effective magnetic field. So before I go into that, I do want to mention that recently these non-reciprocal phases have already been demonstrated by our collaborators, but they are using free space components or bulky RF components, so they are not on integrated platform, which means in the future, if you want to scale this up into a 2D array, it's going to be very difficult to realize those kind of interesting effects. So what we're really looking into is how we can create these non-reciprocal phases on integrated platform. So now I'm going to introduce you to what are the photonic transitions means and how these photonic transitions can use a non-reciprocal phase. And what I mean photonic transitions, which is very similar to atoms, because if you excite atoms with light, you can change the state of the atom from the ground state to the excited state. So in photonic transitions, we're doing very similar things. With external excitation, we can convert or couple photons from the lower energy level state to a higher level energy state. And these energy state will be represented by, for example, optical modes inside the waveguide. And for example, in this drawing, I have a fundamental mode here and a higher order mode here. And you can see the dispersion diagram that at any given k vector, there's always a frequency difference between these two modes, which means that energy per photon is different. So that's why I say the energy levels, different energy levels. So now in this two energy level system, if you have external excitation, this cosine term, and this excitation can be a modulation, for example, and this modulation change the refractive index inside the waveguide, therefore perturb the system, and therefore causes coupling between these two modes. So if the modulation frequency matches the frequency separation between these two photonic states, now the photons in these two levels couple. And the coupling rate depends on this, which is this couple term, depends on how strong your excitation is and how strong these modes overlap. But so far I haven't mentioned anything about the phase. Where does the non-reciprocal phase come from? Well, it comes from the fact that your modulation has a time origin, which is being defined in this cosine term, this phi phase. This phi phase is associated with the time origin of your modulation. And based on energy conservation, we know that the coupling from the lower energy level to the higher energy level, and the coupling from the higher energy level to the lower energy level has to be complex conjugates. Therefore, we know the fact that for the photons that are coupled from the lower energy state to the higher energy state would have a different phase, this phi phase, than the photons coupled from the upper level to the lower level. So basically, the excitation phase is now imprinted onto the photons that experience these photonic transitions. And these phases are non-reciprocal if you're going up versus going down. So this is where the non-reciprocal phase comes from. So now we know that we have a way to generate this non-reciprocal phase. We want to couple these photons in these two modes. But we want to prove that this phase exists. So to prove this phase exists, usually if people want to measure phase, the simplest way to do it is to put things into interferometers and look at the transmission. So all the phase information will now be encoded into the transmission amplitude. So that's indeed what we do next. So we use the interferometer scheme, which takes two of these two-level systems, and we apply a modulator on each of those. So basically, we have a modulator on the left, and we have a modulator on the right. And again, the modulator would modulate the refractive index that will couple photons from either the lower level to the higher level, and from the higher level to the lower level. So for example, in our scheme, we used even and odd mode now instead of using the fundamental and the higher order methods, just because we can get better control of the frequency separation between these two modes. But I will explain that in a little bit more detail later. But if you look at the transmission from the left to the right, if we inject light into the even mode, and in the first modulator, we apply a modulation. And this modulation ideally gives us 50% of light in the off mode and 50% of light in the even mode. And like all interferometers, we like 50-50 splits to get the maximum extinction ratio. And now photons in these two modes will co-propagate and freely propagate in the center region until it hits the second modulator. And before it hits the second modulator, because of the change of the waveguide geometry, they might pick up a phase difference. The photons in these two modes might pick up phase difference that's been noted in delta phi p. And at the second modulator, again, we do the same thing. We apply a modulation, and then we can recombine the photons in these two modes, and we can, in the end, we can probe the output of either of these modes. In this case, we are probing only the even mode. So the non-reciprocal phase would create a non-reciprocal fringe in this case, because you would expect for this kind of interferometers, you would get a amplitude of cosine of delta phi, and where delta phi is total phase accumulated in this interferometer for the two photons in these two different paths. So if we look at from the left to the right transmission, you'll see the total phase accumulated will be minus phi L plus delta phi P and plus phi R, which is the upper arm, which I'm looking at the upper arm of this transmission, whereas the lower arm didn't really gain anything. And if you're going backwards, now the phase is in opposite sign, because now you're gaining a minus phi R and plus delta phi P and plus phi L. So if you look at the fringes of this interferometer, you will see the left and right transmission and right to the left transmission would have a different pattern, different fringe pattern, basically offset by some phases. which is defined by the phase difference between these two modulators. Excuse me. So I would like to just pause a little bit and say why we call it photonic Ramsey interferometer. Because it resembles a lot with the traditional Ramsey interferometer, because if you look at what Ramsey interferometer is, which is coming from the atom source, you split the atoms into a superposition of two modes using the first laser, and you recombine them in the second laser. And this is essentially how atomic clock is built. So that's why, hence, we use the word photonic Ramsey interferometer. So the next question is, how do we implement this in an on-chip platform? So we implement this using silicon photonics, because silicon photonics allows us to modulate light, or the refractive index of silicon, very easily, as I will show you a little bit later. So this is the overview of our device, and this is only a cartoon. It's a sketch. It's not the real device, so they are not drawing scale. But however, you can see it's very similar to the schematic shown on top, which you have two modulators separated in space, and you can see that now, because we need an even and odd mode, we're actually using the coupled silicon waveguides. So if you look at the right, this is the mode profile of the even mode, and this is the off mode in a silicon coupled waveguides. So this coupled waveguides now simultaneously support two modes, one even mode and one odd mode. And photons would have a chance to propagate either in this even mode or this off mode. So again, you have a modulator on the left that can apply a phi L phase, and a modulator on the right, you can apply a phi R phase. And in the center, we change the geometry of the waveguide so that we can generate this delta phi p, which is the phase shift of between the photons in these two optical modes. And just all you need to remember is this delta phi p is now linearly proportional to LF, and as this LF number will come up later. And on the other end of our devices, we have multi-mode interference devices here and here. So these devices are making sure that we're only injecting or probing the even mode, just like what the schematic drawn over here. So I haven't talked about what the modulator looks like. So let's take a closer look at the modulator. So this is the modulator. Again, we have the even and odd mode. Because we need to couple the even and odd mode inside the modulator, we have to make sure the modulation is not uniform, because these even and odd mode are orthogonal to each other. So this is the equation, which is just overlap integral, that tells you how much coupling is between the even and odd mode. And this delta epsilon is your modulation strength. So you can see in this equation, if your modulation is uniform, because even mode and odd mode is uniform, the coupling becomes 0. So you want some non-uniformity along the x-axis. So to do that, we use this PNP diode, as demonstrated here. So as voltage is applied across these two P regions, and as shown also in the bottom center graph, as you apply a sinusoidal voltage, you can see that at any time instance, the depletion width of these PM diodes only opens up in one side of the waveguide. So therefore, that guarantees that even an odd mode will have a non-zero coupling. And if you do this overlap integral calculation, you can exactly calculate what's the strength of this coupling. And again, this coupling strength would mean what's the coupling rate between these two optical modes. So let's look at what we should expect from this device. So again, we have phi L and phi R, which are the modulation phases. And a very important thing is this fire and fire needs to be synchronized, and that can be easily done in the laboratory setup. And if you have this kind of device, in front of the device, you should expect a fringe pattern. And this fringe pattern in the x-axis is the phase difference between phi L and phi R, and the y-axis is this optical transmission. So, but what's interesting is if we have a non-reciprocal phase, which means if the phi L and phi R indeed impart a non-reciprocal phase on the photons, we should see that these fringes are also non-reciprocal. In this case, the blue is the left-to-right transmission, and the red is the right-to-left transmission. So you should see that these two fringes now become non-reciprocal. If it's non-reciprocal, it's a clear indication that we are in fact generating a non-reciprocal phase in each of these modulators by phi L and phi R. So here are the experimental results. So we see in all three cases, we see clear non-reciprocal fringes, although the fringe extinction ratio is a little bit low. But the error bar of this experiment is very small. And we can see in all cases, these fringes do not overlap with each other entirely. And let me explain a little bit more. So the blue dots are the left-to-right transmission, and the orange dots are the right-to-left transmission. And the solid curve is the theory calculation. So what differentiates between these three graphs is different LF value. And if you could remember, LF means the amount of phase shift in the center between the two modulators. And based on theory, these non-reciprocal fringes should move according to the value of LF, and it should be a linear relation. So we also show this. So in the y-axis here, we plot the fringe phases between the left-to-right transmission and the right-to-left transmission. And in the x-axis, we plot LF value, and we do see that these experimental points, which are these blue points, they match pretty well with the theory curve, which is this black curve. And this gray region, which is shown here, is the theory curve that accounts for the plus and minus 5% of the process variations. So see that all the experimental data lies within this process variation. So we also measured all non-reciprocal phases across the 20 nanometers of wavelength range, which is pretty encouraging. The main reason for its quite a broadband operation is because now the even and odd mode dispersions are quite small. So the even and odd mode group index, they are very similar to each other. And you might not be satisfied with the fact that we're getting a very small interference fringe visibility. So to further increase this visibility is to try to increase the RF power. So for the top case, when you only have 3% of the photons in the odd mode because we didn't apply enough RF power, we get a little bit of this fringe extension. And as you can see, once we increase the RF power, we can get 6% and 12% of these photons coupled into the odd mode. So therefore, we are increasing the fringe extinction ratios and the fringe visibilities. So, in conclusion, I've demonstrated a effective gauge potential for photons on chip using silicon photonics, and based on the device length is about 8 or 9 millimeters, so we can calculate the total non-reciprocal phase shift is around 443 degrees per centimeters. And these number match is pretty much the same order of magnitude as the monolithically integrated macroscopic materials. So I hope in this talk I convinced you that using silicon photonics we can create these non-reciprocal phases, and the future work would be trying to use these non-reciprocal phases and try to use these phases to generate a two-dimensional effective magnetic field. And I thank you for your attention. I thank my sponsors, and if you have any questions, I can answer. Thank you.
Thank you so much, Lawrence. And if anyone has any questions, please feel free to type it into the box, and Lawrence will read the question and then answer it. All right, if we don't have any questions, then let's thank Lawrence. He did a great job. And also I wanted to remind everybody that we'll be having a special speaker next week as well. This will be Dr. Chris Mack, who is a scientist, associate professor at the University of Texas, Austin, and also editor-in-chief of the Journal of Micro-Nanolithography, MEMS, and MOEMS. And he'll be speaking about how to get published and how to write the best science paper you can write, even if you don't feel that you have the best writing skills. So I think it's going to be a really great and useful talk. So thank you again, Lawrence, and have a great day, everybody.
No problem. Thanks, Amy. Bye.